In question 4, we have a particle projected from the foot of an inclined plane, which makes an angle alpha with the horizontal. Here's my inclined plane and my angle alpha, such that tan alpha is equal to 1 over root 2. Put it in and find out what cos and sine are. Opposite over adjacent, square root of 3, 1 squared plus root 2 squared. So cos A is equal to root 2 over root 3, and sine A is equal to 1 over root 3. The angle, the initial velocity is u, so we have u meters per second, and at the same angle alpha to the plane, same angle. So my initial vector is going to be u cos A in the I direction plus u sine A in the j direction, which is going to be root 2u over root 3 in the I direction plus u sine A u over root 3 in the j direction. My accelerations are going to be minus g sine A in the I and minus g cos A in the j. So fill that in, minus g by the sine of A minus g over root 3, and minus g cos A is minus root 2 g over root 3. Well, we're asked to prove that the particle lands at right angles, so we're looking at the velocity. But first of all, we need to find how long it takes to land. So when s of x is equal to 0, we have our ut plus a half at squared equals 0. So u sine A u over root 3 times t minus the acceleration in the j direction, root 2 g over 3, and we have a 2 for the half, so it's going to be root 2g over 2 root 3 times t squared equals 0. Factoring out t, we get u over root 3 minus root 2 gt over 2 root 3 is equal to 0. So my initial time of flight, and I'll get u over root 3 is equal to root 2 gt over 2 root 3. We can multiply both sides by root 3. We get 2u divided by root 2g is equal to the time taken. So let's get the velocity of x and the velocity of y. Velocity of x, u plus at. We're going to have root 2u over root 3 my initial velocity in x up here, and then minus, so it's basically minus at or plus the acceleration, which is in the I direction, minus g over root 3 times t, which is 2u from above over root 2g. So this is going to give root 2u over root 3 minus 2u over root 6. And we can simplify this as a simple fraction. Root 6 by root 2 is root 12, which is 2 root 3 u, and then minus 2 root 3 u, makes sense, all over square root of 18. So this is going to give me a 0 velocity of x, unless it, are we asked about it, does it hit the plane at right angles? prove that the particle lands at right angles. Okay, so that's what we've proven by showing the velocity in the x direction is equal to 0. Landing down like this. At right angles, there's only velocity in the j direction. Find the range of the plane, part 2. So the range, we're looking at s of x. We have s of x here. That actually should be s of y. I'm sure you noticed earlier. So s of x. So s of x, u plus at. If you're not going on here, the u is root 2 u over root 3. The acceleration was minus g over root 3. We're taking it from v of x here. So we have ut plus a half at squared. I'm getting distracted. So we have our u times our t, which is the 2u over root 2g, and then minus the 1 over 2. The acceleration is g over root 3, and the t squared is going to be 4u squared over 2g squared. So I can cancel this guy and that guy. So I'm going to get 2u squared over root 3g minus 2u squared over 2 root 3g. Both over 2 root 3g. I'd have to multiply top and bottom here by 2, so this would be a 4 on top. 4u squared over root 3g, 2 root 3g minus 2u squared over 2 root 3g just gives 2u squared over 2 root 3g for the range, and that simplifies to u squared over root 3g. The last part of this question: show that the principle of conservation of energy holds in this case, i.e. that the sum of the kinetic and potential of the particle is the same at the moment of takeoff and of landing. Okay, let's see what's going on here. The particle is taken off and has landed up here. So it's landed a height above the horizontal. And the distance it has travelled is the range, which is u squared over root 3g, and the angle A is in there, and we were told that the tan of A is equal to 1 over root 2, so we got the sine of A to be 1 over root 3. So we would say sine A is equal to h over u squared over root 3g. So the sine of A, which is 1 over root 3, times u squared over root 3g will be equal to the height that it's reached above the horizontal. So that's going to be u squared over 3g being the height. So we can get mgh. So at the beginning, we probably should have wrote what it was at the beginning. So it's your kinetic a half mu squared, and we have mgh. So 0. And we just have a half mu squared, so that's the total energy at the beginning because of the height being 0. So is the potential and kinetic energy at the end the same? So we need the velocity in the y direction to know what speed it hits at. We saw that the velocity in the x direction was coming down at a right angle, was 0. So the velocity in the y direction, u plus at, u was u over root 3 from above. The acceleration was minus root 2 over root 3 times g, and the time taken to get there from above was 2u over root 2g. So we'll end up with u over root 3 minus 2u over root 3. So a u minus a 2u is going to be a minus u over root 3. The velocity at impact, the velocity in the y direction. So a half m v squared is this u over root 3 to be squared, plus mgh is going to be m times g times h, which is u squared over 3g. That's where the g's will cancel. So we're going to get mu squared over 2 times 3, which is 6, plus mu squared over 3. So that's a sixth and a third, which is equal to a half, which is mu squared over 2. Therefore, principle of conservation of energy applies in this case, QE.